Hello, I hope you guys are well. I had a question asked about how I deal with determining the solubility of reactants and products. And the best answer I can give you is that it takes time to get used to reading out what the states of reactants and products. And the best way that you can get good at it is to just practice. It involves using your periodic table, it involves using the solubility guidelines, and it involves using common sense, which I know is always scary because students are thinking, what exactly do you need me to know, et cetera, et cetera. So let me just give you an overview. All right, so I tried to find a copy of our solubility guidelines and it looks awful. And already my videos look a little fuzzy, so I'm not going to use this other than saying that essentially what is said in this table is exactly what's said in this table here. Okay, so you'll notice that nitrates are all soluble. Acetate is, all of them are soluble except for silver acetate, and then chlorine, bromine, iodine, and most of the sulfates are soluble except for some exceptions. And then the mostly insoluble compounds are the ones with sulfides, carbonates, phosphates, and hydroxide. This one I prefer up here because even though it takes a little bit more to get used to, I feel like there's more contained with it, even though I guess there's sulfites in it, and I think that's about it. It also says in this rule here, all acids are aqueous. Anything with the alkali ions, lithium, potassium, rubidium, francium. Does it say calcium? I can't read that. Might be say calcium. All of those ones are also always soluble. It shouldn't, oh, cesium, that's it. Okay, sorry, I had a little mental lapse there because I know that calcium hydroxide is solid. Anyways, so just always check your solubility guidelines. Oh yeah, and then the other one is ammonium. Ammonium makes, the ion makes most things soluble. And everything else, you have to just check your guidelines. And these ones up here, you're looking at the cations. So for the ones that are always soluble, you're looking at these cations, but rules 2 through 8, you're looking at the anions, at the negative portion of the ionic compounds. All right, so I was asked, there was a couple of questions where I have metal oxides, and someone said, well, how did you know what the state of the metal oxide is? And to be completely honest, either I guess or I have it memorized somewhere in the back of my brain, but the only metal oxides, generally they are solid, except for sodium, potassium, strontium, and barium. Calcium oxide is slightly soluble, but all the other ones are insoluble, other than sodium and potassium, strontium, and barium oxide. And so if you mess one of those ones up, you'll probably not be given a question that has an oxide being produced in the context of a quiz or a test. You're going to be given something off of your solubility guideline. The other question is, when can you deem a reactant not to be aqueous? And it's usually going to be indicated in the question. It's either going to say like solid calcium hydroxide or solid iron oxide, something like that, if you read the question. Other than that, if it's an ionic compound and it's reacting, you are going to assume that it is aqueous. Okay, so general rules. It took me a couple of hours. Like I kind of just hemmed and hawed and did nothing this morning. But in the back of my mind, I was thinking, okay, how do I actually go about answering the solubility, or thinking about solubility when I answer questions? So my general rules is that all reactants for double displacement reactions are soluble or in an aqueous form. So either chemists forced it to be soluble, or you can just assume that it's aqueous, and that for the purposes of our course and for grade 12, that is completely fine. So anything on the left side of the chemical equation, say that it's aqueous. Now, for the product side of the double displacement reaction or any reaction, that's when you have to either use your solubility guideline, you have to look at the periodic table, although double displacement reactions, there shouldn't be anything off the periodic table, or use your own common sense. Like H2O, it's going to be liquid, right? That's even if you shouldn't put aqueous, but it should be liquid. CO2, if you get a product from the decomposition of carbonic acid, CO2, it's going to be gas. That's the whole point of further decomposing those products. For single displacement, the reacting ionic compound is always going to be aqueous, okay? So what that means is, let me just change my color. So for this one here, when I'm looking at the below example of gold chloride reacting with silver, I'm not even going to think about whether it's solid or not. I'm just going to assume that it's aqueous. And then when I'm looking at silver, how do I determine what state it's in? I'm going to say that it's solid based off of the periodic table. It's not mercury, so any other metal is going to be solid. Okay, so on the next side, silver chloride, I'll change my color again. This one here, you have to check your solubility guidelines. So when I'm looking up here, I'm looking chloride. Oh, look, silver is one of my exceptions. So always check your products. So this one is going to be solid, and then gold is going to be solid as well. So you might think, oh, am I just going to have a beaker of solid? No, you're going to have a beaker filled with two different precipitates, solid gold precipitate and solid silver chloride precipitate, and then the water that was used to react in it. To give a couple of examples just to go through, because I know that I feel bad for a lot of people because they missed a lot of this unit. So let's try a couple of example questions. Let's try a single displacement. So I'm going to take, let me see, let's take iron hydroxide. No. Let's take iron. I should have really thought of these before. Plus, let's do lithium. Okay, so this is what the question is going to look like. You know that lithium is able to displace iron, and so it's going to kick it out, and you're going to get lithium chloride plus iron, just iron by itself. Looking at your periodic table or just common sense, you know that the only metal that is liquid at room temperature is mercury, so I can just say that it's solid. I have to balance this as well, so I need 3 of these and 3 of these. And then looking at your solubility guidelines, you can see that lithium chloride is going to be aqueous. All right, let's try a more complicated one. Let's do sulfuric acid with ammonium sulfite. So when we have a double displacement reaction here, it's the cation displacing the cation. And so the first product I'm going to have is ammonium sulfate. And if you remember from rule number 1, every ammonium compound is going to be aqueous. And then I think in rule number 1 as well, every acid is also going to be aqueous. Now, common sense or chemistry knowledge, you have to remember that sulfurous acid, it further breaks down. So yes, I'm going to have this aqueous ammonium sulfate being produced, but the reason why this reaction proceeds is because you have H2O plus SO2 formed. You have to remember that water is going to be considered a liquid, and you have to remember that SO2 is considered a gas at room temperature. You need to have knowledge that H2SO3 breaks down into H2O liquid plus SO2 gas, that NH4OH, which is aqueous, this is aqueous as well, it breaks down to NH3 plus H2O. This is a liquid, and NH3 is gas at room temperature. Again, that's why it breaks down. And then the last one that you have to know is carbonic acid. Breaks down to H2O liquid plus CO2 gas. Okay, so some other ones that I might expect you to have some common sense knowledge about. CH4. This is methane. It's a gas. What other ones would I expect you to know? I try not to make too many expectations. I might say glucose. C6H12O6. And you should know that glucose at room temperature, it's sugar, it's going to be a solid. But really, if you read the question, it will help you guide, or it'll help guide you. So you might be like liquid hexane reacts completely with oxygen. Okay, so from that, you know that hexane is going to be liquid, and oxygen, off your periodic table, pure oxygen is going to be a gas. Okay, so I hope that that helps you. Please let me know if you have any further questions about that, or if you want me to do a couple more examples.